In Module 6, I demonstrated the use of Google Forms to make a form that allowed me to enter about 770 data points to calculate the volume of concrete required to fill the footings over bedrock for our new sugar house on our property. To give you an idea of what you're going for, here's the frost wall and 2 feet above grade wall will look like for this structure drawn up in SketchUp. The bottom of this follows the footings that we framed around the bedrock. Let's start with a generic example of calculating footings, because calculating volume of a complex structure may be new to people. I have 2 walls that are 36 feet plus 13 inches, or 2 times the 6.5 inch extra width, and 3 walls inside those 2 walls that are 24 feet minus the part of the 36-foot walls that cut into them, which is 19 inches minus 6.5 inches, or 12.5 inches on either end. Now, I have gone in my SketchUp program and pulled measurements of these lines. But we don't often have that. A lot of times we're going to be doing our calculations here in our spreadsheet. And we're going to calculate volume with inches because the fractions of a foot will work out oddly. I think you're just going to have to trust me on that. But we're going to calculate in inches and then we'll work from there. So our east and west walls are this wall and this wall. They are the long ones. And their length is 36 feet. So to get that in inches, I'm going to type 36 feet and I'm going to multiply it by 12. Now I'll also have 6.5 inches on either end. I can add them together in my head, or I can just add 6.5 and 6.5. And the length comes to 445 inches. Let's take a look at what 37 feet 1 inches equals. So 37 times 12 plus 1 is 445. So that is accurate. The width is a constant 19 inches, and the depth on a standard footing would be 8 inches. My west is exactly the same, so I can copy those values there. Now, the north, center, and south walls are 24 feet, but they are 24 feet to a point that's 6.5 inches off the outside of these 36-foot walls. So how are we going to manage that? What we need to do is we need to figure that this box is 19 inches wide, and we've taken 6.5 inches off the outside. That's where my 24 feet would measure to. So it's going to be 24 feet minus 19 inches plus 6.5, and that minus 19 plus 6.5 times 2, because it happens on either end. All right, that's a lot, but let's write the formula. So we have 24 feet times 12 to get that into inches. And then we're going to subtract, and I'm going to put this in parentheses because I'm going to do the 19-foot wide footing minus the 6.5 inches of beyond the 24 foot that I'm taking off, and I'm going to multiply that times 2. Everything is in inches. We have a 24-foot wall times 12 to get it in inches. Then we have these 19-inch footings on either side, but 6.5 inches on either end are beyond the overall 24 inches. So I'm going to subtract that 6.5 from the 19. I have it on both sides, so I need to multiply it by 2. Because of order of operations, we're going to do what's in the parentheses first, then we're going to do the multiplication, then we're going to do the subtraction. So that should all work out great. Comes 263 inches. Let's very quickly look at my answer here of 21 feet 11 inches. We'll do 21 feet times 12 inches plus 11. Comes to 263. So that calculated correctly. My width, again, is 19. My depth would be 8. And I could take that and I can copy it to these 2 spots. For volume, I'm going to multiply each part. And I'm going to copy that formula on down, move my picture down, The volume of this piece, this oddly shaped piece, is 255,208 inches. Okay, well, concrete doesn't come in cubic inches. It gets delivered in cubic yards. And let's figure out how we're going to calculate cubic yards from this. Here I have a box that is 1 yard by 1 yard by 1 yard. Now, along this one edge, I've marked every inch. We know that there are 36 inches in a yard. So that's the linear measurement. Now, if I want to get a square yard, or the area of something that is 1 yard by 1 yard, I would multiply 36 by 36. And I would get all these little inches on here. And then if I wanted to get volume, it's going to be 36 times 36 times 36. It's a lot of little 1 inch cubic boxes stacked together to make a cubic yard. Let's look at that mathematically. So a linear yard is 36 inches. A square yard is 36 times 36, or 1,296 square inches. And a cubic yard is 36 times 36 times 36 inches, or 46,656 cubic inches. We could divide this number by this number. I often find that I'm not going to have that number kicking around. So what I can do is I can take this value here and I can divide it by 36 three times. And that will do the same thing. I need 5.46 cubic yards. And if you want to see what this number divided by that number equals, we can just do this divided by this. We should get exactly the same value. I wanted to go through the process of showing you visually how we calculate cubic yards from cubic inches so that you can see how we're doing that and how these values equal each other, and working our formulas in different ways can also work. Normally, I would also do a 10% overrun. So I would take this value and multiply by 1.1, and I would order 6 cubic yards for a classic footing like this. I have measured the volume of 5 boxes, and I have come up with a slightly less than 10% overrun of 6 cubic yards. A traditional concrete mixer carries 9 yards. That's where we get the phrase the whole 9 yards from. There are some companies that do run larger concrete trucks these days, but the ones that service me here in Pownell, Vermont, I can get 9 yards. So if I need more than 9 yards, I need to get more than one truck coming. Now let's go ahead and look at our more complicated scenario. Even if I wasn't working on bedrock, if all of these different footings were all even on the bottom, I would have a lot more boxes to calculate. Here is that same drawing with just the surface of the footing showing. And here, what I'm showing in this illustration, this yellow part is the wood from my forms that are going to hold the concrete in. And these lines here in the middle, they're showing where the wall is actually going to sit on the footing. And this surface is measurable and easy to work with, but the part that's below it is what makes this calculation really challenging. This is a photo of one of the spaces along the footings that we built. Of course, we are in the process of building these because the box isn't completed here, but this is a good place to show you how we measured things. We would put the story stick here where this blue line is at this point, then at this point, and we need to measure the area below those blue points, and then knowing the area of those two places, we can then calculate the volume of the space in between. From this blue line, we'd measure down at the 0 side and at the 19-inch side and get those measurements. And this looks pretty even throughout. And when we think about then also measuring down at this point from side to side, we wouldn't need to take interim measurements on that story stick. Just the 0 and the 19 are going to work. And I'm going to show you mathematically how knowing this area and seeing that it's kind of a plane between those 2 points, we can actually calculate this volume of this box made by these two sides. Let's now take a look at the spreadsheet which holds the data entry made out in the field. Here on the south wall, we started at one end, and the end that we started at is at 0 inches. And at the 0 point on the story stick, the depth measured 4.5 inches. And at 10 inches on the story stick, it measured 6.5 inches. And then at the far side, at 19 inches, it measured 7. And then we moved 7 inches away because that's where things changed. And we took another set of measurements along the story stick with measurements on either end and anywhere in the middle where there was a significant change. So we can see here on one side of the footing it was 8.5 inches deep, and on the other side it was 8.5 inches deep. But about in the middle it was 10.5 inches deep. So we need to accommodate for that. So let's take a look at how we use this math now, or these values, along with math to calculate the volume of this little box from 7 inches to 12 inches. So 5 inches apart, 2 planes, their areas, and then calculating the volume between them. So here in Excel, I used a line chart to draw the bottom of the measurements here, because here we are 7 inches from the beginning of the wall. At the 0 mark it's 8.5 inches. At 8 inches across it's 10.5 inches, and at 19 inches across it's again 8.5 inches. And then the 12 inches from the beginning of the wall, at one side of the story stick it's 6 inches. At 10 inches it gets down to 6.5, and it's 6.5 over at the 19-inch side. So these are two ends of a wall, and I'm going to show you how we calculate one end and how things work out calculating area, and we can use the same principles to calculate volume. Most of us would look at this and think we needed to measure this rectangle, and these two triangles. So let's do that. Let's call this rectangle part 1. We know when we're measuring this rectangle that the width is 8 inches. It's 8 inches from the 0 point in the story stick to the 8-inch measurement where we measured down. So it's 8 inches. And its height is 8.5 inches, because that's what we are at the 0 side. And making this a perfect rectangle, that's going to be 8.5 inches. And our area is always our width times our height. And then we can measure this other rectangle here. So this goes from 8 to 19 inches, so that width is 11, and its height is also 8.5 inches. With right triangles, it is the two sides that meet at the right angle, and then we divide it by 2, because if we finish this rectangle out, we would calculate the area as the width times the height, but the angle of the hypotenuse cuts that in half, so it'll be divided by 2. So I'll come out here and I'll make these formulas divided by 2. So I'm going to take that one and I'm going to copy it down to that one. Again, this width is 8 from 0 to 8 inches. Its height, because we're measuring down to 10.5, is 2 inches. And for this triangle, the width is 11 inches and its height is 2 inches. But again, divided by 2. And if we add those up, we get 180.5 square inches for this shape. Now here's the other thing you can do. Since we are dividing this space by 2, we can actually take this line and average them. And if we average them, we would just get basically half the height of this longer one, which makes this work for both sides because we'd only be measuring down to half the height of this bigger rectangle. I did this the long way so we could see when we do it my way that this goes pretty fast. So we have to measure each section where we measured height. That we can't avoid. But we don't have to measure out rectangles and triangles. We can just measure this quadrilateral here that has two 90-degree angles and then these two opposing angles. So our width is still 8 inches. Our height is going to be the height at the 0 point, which is 8.5, plus our height at the longer point, which is 10.5. I think we can actually just call this equals average. 8.5, comma, 10.5. I spelled the average wrong. And then our area is this value times this value, or 76. Now, we can see here our part 1 was this big rectangle, 68 inches, and our part 3 was this little triangle of 8 inches. If we add 68 and 8, we get 76. So we are seeing that this is exactly the same way of calculating the value, just with fewer calculations. So we'll do the same thing for part 2. Our width is 11. Our height is average of 10.5 and 8.5. And when we total this, we get 180.5 inches. We can do the same thing for our 12 inches. This one we're measuring from 0 to 10, so the width is 10 for the first one, 10 to 19 for the second one is 9 inches. Our height equals an average of 6 and 6.5 for the first one. And we can still use this same average, although we wouldn't need to because the values are the same, 6.5, 6.5. They're going to average to 6.5. And we can do a quick sum here. Now, I'm not going to get into the craziness of the math of this, but basically speaking, the same way we can calculate this odd shape by averaging these two ends, we can average these two areas and multiply them by the distance between them to get the volume between them. So the distance between 7 and 12 inches is 5 inches. The area for this end is equal to 80.5. And the area for this one is 121. And so our volume equals the distance between, I've named these cells so they come up in my formula nicely. I just need to have a multiplication sign here because it's not true algebra. And there we go. The area between these two pieces was 753.75 cubic inches. Now what we have to do is do this around the entire space, both the 36-foot walls and the 324-foot walls. There are a couple other things that we're going to need to take into account when we're dealing with the numbers, but this is going to get us to the point where we can use the copying of formulas in Excel to do all these calculations for us. We don't have to go around by hand and calculate every single one of these points where we measured with the story stick. Let's get into that scenario now. As I explained in my first video in Module 6, we made over 770 data point entries using the story stick along the footings, and they are all here in this Google Sheet, which I will share in the description on YouTube for anyone who happens upon this and wants to play around with the spreadsheet work. I'm only going to set it so that you can view it, so you'll have to make a copy of your own, or I would encourage you to download it to Microsoft Excel. In the real world, I did all of these calculations around a campfire on my phone. It took me about an hour to do this in real time using Google Sheets. But I'm going to demonstrate to my class in Excel, so download it in Microsoft Excel. I'm going to switch to Excel now, and we'll get to work on this. So here we are with all of these measurements. There are mistakes in this, and we're going to find a few along the way. I haven't edited the mistakes out because I feel it's important to be aware of your work and know that there's going to be some issues and know how to manage those issues as well. If we were working with a textbook, we wouldn't have these cool features. So I'm excited to go through all of the mistakes and all that we have here. So one of the first things I see is there are a couple blank lines here, so I'm going to go and delete those. I don't know how they managed to show up in my system. I might have submitted the form a couple times by accident. Another thing we're going to see is I asked about, like, is this a second step measurement? And I said yes on these, but I can also see that this is a second step measurement. And let me explain what's going on here. Here we are on that south wall, which I started working with earlier in this video, and we did a measurement 99 inches away from the wall. And then I'm showing here 99.001 inches away from the wall, which, as far as a statistically significant number, this number and this number are the same in our grand scheme of things. So what's going on here? This is where I'm going from one level to another. We can see here at this 99-inch measurement, we measured 0. At the 0 point, we measured 13 inches deep. But for this 99 inches away from the beginning, at 0 inches, we measured 8.5 inches deep. And this is because we are measuring a different box with a different height top in it in the system. And what I decided to do was, rather than try to check to see if I used yes in this column, I'm just checking to see if this value is the same as this value. And when it's not, then I'm going to do different calculations. So I actually do not need column E or column F. I'm going to hide column F. I might as well hide column E. It's easy to bring it back. I have lots of boxes. The boxes we know are all one plane to calculate the area of when they are the same value. So for these three values, I'll have to calculate the area of this plane. And then I'll have to calculate the area of this plane. And then I'll need to calculate the volume between this plane and this plane. And then this plane and this plane, and this plane and this plane. And we'll keep going on down with our formulas as we do that. I know there were a couple of mistakes here, which we're going to find when we have weird numbers in our calculations, so I do kind of just want to get going on that. So we're going to need to use some if functions and a variety of if functions when we're working on this. We already know that when we're calculating the area of a plane, at each point we need to average the depth between the 2 points and multiply it by the distance across. And that's going to give us the area of that space. And we're going to do that for each pair of numbers. So we're going to do it for the 0 point to the 10 point and the 10 point to the 19 point. We're going to average those out. And then ultimately we need to add up all of those areas to make the area for that point. And then we need to start over again. So we're going to work a little bit with logic here. So I'm going to call this individual areas. I don't want to calculate an area at this point, but I do want to calculate one here and here. I don't want to calculate an area at this point because I don't want to go from 19 to 0. This is not an area we're calculating. This is a new space. I'm going to start by doing my calculations in a cell where I know I want it to work. So I want to calculate the area from 0 to 10 inches, where 0 is measured at 4.5 inches deep and 10 inches across is 6.5 inches deep. So let's just do that calculation. So we're going to calculate the area by saying it equals this value minus this value times the average of this value and this value. Now, I do need to put some parentheses around these column C cell references. I'm getting 55 cubic inches there. So I want to do that when this number and this number are equal. So let's put an if sign in, an if function around this. Equals if this equals this, then we're going to do that function. Otherwise, we're going to leave the cell empty for now. And that still comes up with 55. I'm going to go ahead and double click this corner and let it copy all the way down. So this works. That first area is 55 square inches and the second area is 60.75 square inches. That's fantastic. Then I don't have anything for the first 0 measurement on 7, but I do for the next 2. There's 2 for 12, there's 2 for 21, there's 3 for 21, 2 for 24 point. There's only 1 here at 27 inches and so on. We could scroll down and take a look. It all looks pretty good. I don't know why I have... So now this one concerns me. This should have been at distance across 0, and then 19 should have been my second one. Oh, actually I have a 0, a 6, a 12, and a 19. So I think I just have an extra row here. Let's delete that one. It's upset about that, so let's delete this one. All right, let's keep looking to see if there are any other mistakes. That just needs to have a name to it there. I don't think it matters too much. Excellent. So we have all these individual areas calculated. Now, I want to add up these individual groups. Now, the numbers that I'm adding could be one number or two numbers or three numbers. Some of them have, 4 or 5 points of calculations. There aren't too many. There's one with 4. So here I'm going to add plain area. I've set that field to be wrapped. And so what I want to do is I want to add if the values have shared unique points to them. So the two values that make these groups unique are the wall they're on and the distance from the beginning of the wall. So I want to add these numbers if the wall they're on and the distance from the wall are the same. So if I want to add based on criteria, it's going to be SUMIF. I have 2 criteria, so I want to use SUMIFS, SUMIFS. So I'm going to type equals SUMIFS. And the range that I want to add is G. And if I just click on G at the top there, it will put the G:(G) range. It will select all the range. Now the next thing I have is what is the range which I want to have the first criteria on, and it's column A, the wall name. And what is the criteria? Well, here I only want to add if it's also south, and the other range is the distance from the wall. And I only want to add it if it is also 0 for this group of numbers. So let's look at this function and how it works on this spreadsheet. So these two numbers, 55 plus 60 and 3/4 is 115.75. That is correct. And if I double click that autofill, it'll fill all the way down. Now, it is weird that I'm getting some zeros. Let's look at that. I have some points here where I must have the wrong number. This is 285, this is 288, then this is 286 and 287. So clearly I put the wrong number in here. That should also be 288. So let's fix that. So that's better. Let's see if there's any. Oh, here's another 0. Why do we have a 0 here? Here again, instead of typing 117 in the fill-in field, I typed 107 by accident. So let's fix that. Now, even just doing all these individual ones by hand would be a real pain. So here, this is 280.001, and this one I transposed two numbers. So instead of 208, that should be 280. See where else I might have zeros or weird numbers coming up here. Some more zeros. Here in my insignificant digits, I had 2 1s instead of 2 zeros. Let's fix that. There's another 0. Here I switched to the center wall too soon. That should also say north. So we'll put north there, and that'll fix that. Okay, I think we have those errors found and fixed. Now I want to calculate all these individual box volumes. And there's some neat things going on here that'll work great that you'll see when we copy this formula down. So here's our first transition between planes. We've calculated the area of the first plane that we measured, and we've calculated the area of the second plane we measured. And we calculate the volume by averaging these two and multiplying it by the distance between the two of them, which is the distance of the second one minus the distance of the first one. So let's do that. The volume of this particular, between these two particular planes, is the average of this plane and this plane. And we're going to multiply that times the distance between them, which equals the distance from the wall of the second one minus the distance of the wall from the first one. And we'll hit enter. And then we'll go ahead and copy this on down. Look at that. I only get one box volume calculation each time. Why is that? Because when we're here in this cell and we average these two values, but then we multiply them by the distance from the wall minus the preceding distance from the wall, that's 0. And 0 times anything is 0. So we don't have to do any more fancy filtering. If we don't want the zeros to show, we could do another if function, but this is actually going to work. Now, there's only one place, well, actually 5 places that this isn't going to work. Because, as we'll notice when we get down here, and we transition from the south wall to the west wall, we get a big negative number. We have some other negative numbers, so we're going to have to take a peek at that quick. But here we have this huge negative number. Now, we could do a function to determine if these values are different between them and then not show these. But at the moment, I like how simple these functions are, and I only have to do this 4 times. So I'm just going to delete these 4 values that are hugely negative, and then I've got to go find out what's going on with the other ones. So here, when we transition from west to east, we have a huge value that we need to get rid of, a huge negative value. We transition from east to north, we have to get rid of that. And from north to center, we're going to get rid of that one. And center is my last one. So just deleted 4 functions. Could we write a function that would do that for us? Absolutely. And if we were going to use this kind of formula again, we might want to do that. But this is really a one-shot deal for me. I think we've made plans not to make crazy stepped footings again in the future. But I want to see what's going on here. What's going on here is I go from 283 to 285, 288, and then 287. I'm going to guess that this is supposed to be 289. It's not going to make a lot of difference in the grand scheme, but I do want my calculations to be more likely to be correct. It's possible we went backwards and added a 287 after the 288, but we'll just work with that and we'll have 149 cubic inches, which, like I said, in the grand scheme of the volume of concrete here, it's not that much. All right, so now we have the volume of all these little boxes. I do want to just point out here that when I go from 208, for example, to 208.001, we have 0.15 cubic inches calculated here. So we're dealing with these transitions in a really good way, because effectively that's 0. There's no difference between these 2 points, and there really shouldn't be any volume there. To get the total volume here, I'm going to add up the sum of column I. And we have 340,653 cubic inches of volume. We can change that to cubic yards by taking this value and dividing by 36 3 times. 7.3013 cubic yards. I like to have a 10% overrun, so we will just keep working our way out in here. 10% overrun equals this times 1.1, and we get 8 cubic yards, which is what I ordered. If you watched the first video, you would know that after we filled all that concrete, almost 8 yards of concrete, all we had left was that much concrete sitting right there in the yard, which was fantastic. We were really pleased with how the calculations worked out and how the run went. Now you know how to calculate an uneven volume if you need to. Hope you enjoyed this. I'd love any feedback you guys might have either in class or here on the YouTube video.